Hello everyone, I'm Wei Chenggan, an application engineer of Bettersizer Instruments Limited. For years, the Bettersizer 2600 has been a benchmark for particle size analysis, reliable, precise, and robust. But industries evolve, and the demands for wider versatility and higher efficiency are growing every day. Today, I'm proud to introduce the evolution of that legacy. This is the Bettersizer 2600 Plus. We call it the all-in-one solution because it doesn't just measure, it adapts to every challenge your lab faces. Our discussion today is structured to take us from the fundamental why to the practical how. First, we will step back and answer the core question: why measure particle size? Why is this parameter so critical to your product quality? Second, we will look at the physics. We will explore how we measure particle size using the laser diffraction method, establishing the scientific principles that drive our technology. Third, with that foundation laid, we will officially meet the Bettersizer 2600 Plus and see how it embodies these principles. Fourth, we will dive into the specific features and benefits, specifically focusing on optical innovations that set this instrument apart. And finally, we will demonstrate the real-world applications, providing that whatever your industry, from batteries to ceramics, there is a solution here for you. Let's begin with the fundamental question. Let's start with a deceptively simple question. What is the size of a particle? If every particle were a perfect sphere like the one on the top left, this would be easy. But in the real world, your materials are needle-like, porous, or flaky. Measuring a flake with a ruler gives you a different answer depending on how you hold it. This brings us to the most important concept in our industry: equivalent diameter. Look at the diagram on the right. To measure a irregular particle, we must compare it to a perfect sphere that behaves the same way. If we measure how fast it settles, we get a sedimentation diameter. If we measure how it passes through a mesh, we get a sieving diameter. But with the Bettersizer 2600 Plus, we use laser diffraction. This gives us the volume equivalent diameter. We are asking, what is the diameter of a sphere that has exact same volume as this particle? This is the industry standard because it is the most robust way to quantify the amount of material you actually have. So, why is equivalent diameter the most critical number in your lab? Because it dictates behavior at three distinct levels. First, at the micro scale, here, particle size changes the intrinsic behavior of your material. As we go smaller, the specific surface area skyrockets. This doesn't just change reaction rates, it fundamentally alters properties like catalytic activity and dissolution. If you change the size, you are effectively changing the material itself. Next, at the mesoscale. Here, the distribution decides the structure and uniformity of your product. If you have a narrow distribution, particles are similar in size. They stack easily, forming a regular, ordered packing structure. But if you have a wide distribution, small particles fill the gaps between the large ones. While this improves packing density and compactness, it introduces a risk. If uncontrolled, it leads to spatial inhomogeneity and reduced product consistency. Finally, at macro scale, this is where size control determines process stability. Look at the flow behaviors on the right. If you have too much fine powder, cohesion takes over. You get bridging, arching, and wrestling. Conversely, If the distribution is wrong during compaction, you get defects like lamination and capping. We established why measuring particle size is critical. Now the question is, how do we measure it? Looking at the landscape of particle sizing technologies, you have specific tools for specific extremes. For the ultra small, down to the nanoscale, we rely on dynamic light scattering like the B nano. For shape analysis of coarser materials, we look to image analysis like the BVision series. But for the vast majority of industrial applications, you need a workhorse, a single technology that can bridge these worlds. This is where laser diffraction dominates. Focus on the green arrow at the bottom. This is the domain of the Bettersizer 2600 Plus, with a massive range from zero point zero 0.02 microns all the way up to 3,500 microns. This is single instrument captures the entire spectrum. Whether you are analyzing submicron battery slurries or millimeter-sized mining aggregates, the 2600 Plus handles it all without changing techniques. So, how does it achieve such a wide dynamic range? Let's look at the physics. This is what happens inside the optical bench when we press Start. When a laser beam hits a single particle, it doesn't just block the light like a shadow. It creates a complex interaction. Look at the diagram on the left. The light undergoes four distinct physical changes simultaneously. It bounces off the surface, which is reflection. It bends as it passes through, so-called refraction. Some energy is lost inside the particle, the absorption, and importantly, it bends around the edges, that's diffraction. While the industry calls this laser diffraction, we are actually capturing the sum of all these interactions, which we call light scattering. All of this scattered light travels outward to create a unique pattern like the one you see on the right. This pattern is the fingerprint of the particle, and as we will see next, the shape of this fingerprint tells us exactly how big the particle is. Now, let's isolate the most important interaction, diffraction. This is the core principle the Bettersizer uses to calculate size. Imagine a simple setup, a laser source, a single particle in the center, and a detector screen behind it. When we fire the laser, the light hits the particle and bends, creating a diffraction pattern, a series of concentric rings on the detector. Now, watch the animation carefully. As the particle changes size, the pattern breathes. You will notice a fundamental counterintuitive behavior. As the particle gets smaller, the pattern gets bigger. As the particle gets larger, the pattern gets smaller. This is the inverse relationship that drives our entire industry. Let's freeze that motion to make it clear. Look at the top. A small particle scatters light at wide angles. The energy is spread out, creating large, faint rings. Look at the bottom. A large particle scatters light at the narrow angles. The energy is concentrated, creating small, intense rings. This is the golden rule of laser diffraction. Small particles, large angles. Large particles, small angles. The Bettersizer 2600 Plus measures these angles and intensities precisely, then works backward to tell you exactly how big the particle is. But to do that accurately, you need an optical system that can catch all those angles. Let's put all those pieces together into a complete system. This is the workflow of every measurement you will ever run. Follow the red beam from the left. The hardware. When we fire the laser source, it passes through the sample cell, where it hits your particles. As we just learned, the light scatters. The optics. As the scattered light passes through the lens, which will focus it onto our array of detectors. Then the data. The detectors take that physical light and turn it into a digital electrical signal via the signal converter. At this point, we don't have a size yet. We have what you see in the bottom right, a scattering spectrum. This is the raw data, intensity versus angle. This is where the algorithm of the Bettersizer takes over. The software performs an inversion calculation. It asks a complex mathematical question. Based on the Mie and Fraunhofer theory, what combination of particle sizes would create exactly this spectrum? It works backward from the light pattern to the particle reality, and the result is what you see on the bottom left, your final particle size distribution. So, the quality of your result depends on two things: precise hardware to catch the light and a powerful algorithm to decode it. Now, let's take a glance at the Bettersizer 2600 Plus system. It adopts a flexible modular design consisting of the main unit, a dynamic image analysis module, and a comprehensive range of wet and dry dispersion modules. A key upgrade here is the integration of laser diffraction and image analysis. With the optional Peak 1 module, it measures particle size and shape simultaneously, extending the upper measurement range to 3,500 microns. Whether for suspensions, emulsions, or dry powders, this versatile system covers it all. Here are the detailed specifications of the system. The Bettersizer 2600 Plus covers a measurement range from 0.02 to 2600 microns with excellent repeatability of less than 0.5%. It utilizes a patented optical design that combines Fourier and inverse Fourier setups with a tilted sample cell to ensure high accuracy. With the optional Peak 1 module, it adds dynamic image analysis, extending the upper measurement limit to 3,500 microns and providing particle shape information. These robust specifications allow it to handle both wet and dry measurements with high precision. Now, let's explore the patented optical design of the 2600 Plus. A high-power 635 nanometer red laser source illuminates the particles, generating scattering patterns captured by 92 detectors. These detectors are strategically arranged in forward, lateral, and backward positions to cover a massive detection range from 0.016 to 165 degrees. The system integrates two key patented technologies: the combination of Fourier and inverse Fourier designs and the tilted sample cell. This architecture is the foundation of our high precision and wide dynamic range. To appreciate the innovation in the 2600 Plus, we must first understand the two standard optical designs used in our industry. First, look at the Fourier design. Here, the lens is placed after the sample cell. The advantage is high resolution, as we can change lenses to focus on specific ranges. However, it has a major limitation. Because the lens has a fixed aperture, it physically blocks wide-angle light. This means it cannot detect very small particles effectively. Conversely, we have the inverse Fourier design. Here, the lens is placed before the sample cell. This allows the detectors to capture wide-angle light without obstruction, making it excellent for small particles and broad ranges. But it has a weakness. the resolution is lower, and the optical path is strictly limited by the detector layout. For decades, manufacturers had to choose one or the other. You either got resolution or range. But we ask, why not have both? Here is how we integrate these concepts into the Bettersizer 2600 Plus. It begins with the laser source illuminating the sample cell. First, we apply the Fourier design to backward detectors. By placing a lens after the cell in this specific path, we effectively capture the high-angle backscattering signals. Next, we utilize the inverse Fourier design for the frontal and lateral detectors. By positioning the lens before the sample cell, we generate a focused beam that allows these detectors to capture signals across a broad angular range without obstruction. This specific arrangement, inverse Fourier for the front and side and Fourier for the back, is the key to our optical performance. This patented combination allows us to detect particles from 0.02 to 2600 microns in a single scan. We don't need to change lenses or move the cell. The unique synergy of these two designs ensures that no particle, large or small, goes undetected. Now, we face a fundamental physical limit of a standard optical design: total internal reflection. In a typical straight cuvette, when light scatters at very wide angles, which is the specific signature of very small particles, it hits the glass-air interface at a shallow angle. As you can see from the green dashed lines, this light cannot escape. Instead of passing through the detectors, it hits the critical angle and reflects back inside the cell. The result is signal loss. Because the lateral detectors never receive this data, the system effectively goes blind to the finest particles. This missing information confuses the algorithm, leading to a shift in particle size distribution peak and reduced accuracy in the micron to submicron range. The solution is our patented tilted sample cell technology. By tilting the cuvette, we shift the angle of the glass wall relative to the scattered light. Now, look at the blue beams on the zoomed-in cell. Because of the tilt, they no longer hit the critical angle. Instead of reflecting back, they pass straight through the glass to the lateral detectors. This geometric change eliminates signal loss, ensuring that every particle can be accurately detected. To use the Mie theory effectively, you need accurate optical parameters, specifically the refractive index. Usually, this is a guessing game. If you don't know the index of your new material, your results are compromised. The Bettersizer 2600 Plus solves this with a dedicated refractive index measurement function. Look at the screenshot in the middle. The system analyzes your sample and calculates potential refractive index values. It then assigns a credibility score to each one, shown here by the green bars. You simply choose the value with the highest credibility. As you can see in the table, our measured values match the theoretical standards almost perfectly. We turned a complex optical question into a simple, confident choice. However, laser diffraction has a blind spot: irregular particles. While the Mie theory assumes perfect spheres, the real world is full of irregularities like fibers and flakes. Here is the physical reality inside the sample cell. First, consider fibrous particles. In the flow field, shear forces pull these particles straight, causing them to align parallel to the flow direction. As a result, the laser only sees their lateral cross-section, missing their true size. Second, consider flake-like particles. These tend to orient themselves with their largest surface area facing the beam. This causes the instrument to capture an equivalent projection that biases the result toward a large size while losing critical shape information. Because of this preferred orientation, the scattering pattern loses its circular symmetry. The result is a distorted measurement, a 1D number trying to describe a 3D complexity. To truly understand properties like flowability or coating performance, calculating size isn't enough. We need to see the shape. Now, let's look at the optical architecture of the Peak 1 module. Everything begins with stability. The particles are stably transported by the dispersion system into the imaging channel. Once inside, they pass through an optimized optical layout featuring two distinct passes. We utilize a 0.5 time magnification for coarser views and a 10 times magnification for fine details. Crucially, these two passes can acquire images synchronously or independently. This flexible design ensures that we can achieve high-resolution observation of both particle shape and size regardless of the sample complexity. Consider samples like river sediments or soil. These irregular particles violate the equivalent sphere assumption of laser diffraction, creating an inherent observability limit where the model calculates a diameter but misses the physical reality. The Bettersizer 2600 Plus does not just improve accuracy, it breaks this limit entirely. By integrating dynamic image analysis, we stop estimating and start measuring 32 distinct morphology parameters, including circularity and surface roughness, to capture the true nature of the sample. This solves the critical blind spot of traditional diffraction, distinguishing tails in your data. You can now visually confirm if a deviation is a rigid aggregate affecting quality or merely an air bubble, providing the physical verification that statics alone cannot offer. Precision optics require precision delivery. We adjust the physical diversity of your samples from heavy sediments to precious pharmaceuticals through a modular dispersion architecture that adapts to the material's nature. For routine, broad distribution materials, the BT812 is the robust standard. Its high circulation volume and speed are engineered to keep heavy or poorly dispersed particles in stable suspension, ensuring the sample reaching the laser is statically representative. However, when chemistry or scarcity dictates constraints, we swap the module. The BT80N series provides chemically resistant pathways for organic solvents and acids, while the BT814 handles high-value microsamples. By removing circulation lines, the BT814 requires only milligrams of powder, making it indispensable for R&D when sample quantity is limited. Let's analyze the engineering logic behind these specifications. For standard applications, the BT812, the top row, utilizes a large 500 milliliter volume and a dual impeller design. This is not arbitrary. It is physically necessary to prevent the sedimentation of large, heavy particles in broad distributions. However, when using organic solvents, volume becomes a liability. The BT80N series reduces the operational volume to as low as 80 milliliters. This minimizes your consumption of hazardous or expensive media when retaining the automation required for reproducibility. Finally, for precious samples, look at the BT814. By removing the circulation loop and using a static 8 milliliter cell, we lower the sample requirement to just 1 milligram. This table confirms that we have a solution for every sample constraint. Let's deconstruct the wet measurement ecosystem. It is not a static snapshot, it is a dynamic, closed-loop cycle. On the left, you see the architecture. The sample is driven from the circulation tank through the measurement cell where it intersects the laser and then recycled. This continuous flow ensures that the snapshot the laser sees is statistically representative of the entire bulk sample. But flow alone is insufficient. On the right, we see how we actively manipulate physics to ensure a true dispersion. First, gravity. Large, dense particles naturally settle. We counter this with stirring and circulation, creating a mechanical suspension that maintains total homogeneity. Second, van der Waals force. Fine particles inevitably cluster into agglomerates. We inject ultrasonic energy directly into the tank using cavitation to shatter these clusters and drive out trapped air bubbles that would distort the data. Third, surface tension. Many samples are hydrophobic. We introduce chemical surfactants, anionic, cationic, or non-ionic, to lower the surface energy, ensuring the water accurately wets the particle rather than repelling it. For hydrophobic samples like graphite or sulfur, manual sample preparation is the biggest enemy of repeatability. One drop of surfactant varies by operator, leading to bubbles or floating powder. The BT812 solved this with automatic surfactant dosing. You simply connect your surfactant bottle directly to the unit, and the system automatically injects the precise volume required during the dispersion cycle. Crucially, this is paired with a real-time stability check. The software monitors the optical signal and will only trigger the measurement once the particle distribution stabilizes. This guarantees that your sample is fully wetted and dispersed before we capture a single data point. For samples that dissolve in water or react with solvents, wet measurement is physically impossible. In these cases, we switch to dry dispersion, relying on aerodynamic shear force to separate particles. The BT912 is the standard for bulk powders. It utilizes an electromagnetic feeder to ensure a constant feed rate, driving the sample through a venturi nozzle where compressed air, nitrogen, or noble gases shatter agglomerates instantly. For scarce materials, the BT903 is the engineered solution. It miniaturizes the flow paths to require only 20 milligrams of the sample, ideal for early-stage pharmaceutical R&D. Both units relied on a dedicated air compressor and vacuum system to maintain stable pressure and ensure zero laboratory contamination. Let's consult the specifications to select the correct dry module. The BT912 is the industrial standard designed to handle up to 10 grams of powder. This large mass is statistically vital for heterogeneous bulk materials where a small sample would be unrepresentative. However, for pharmaceutical R&D where the material is scarce, the BT903 is the logical choice. It reduces minimum sample requirement to a mere 20 milligrams while maintaining the exact same dispersion pressure range as the larger unit. This is a critical engineering detail. It allows you to develop methods on the BT903 in the lab and seamlessly scale up to the BT912 in production without changing the dispersion physics. A stable dry measurement requires a balanced pneumatic circuit. The air compressor drives the sample through the venturi nozzle using a compressed air or inert gas, while the vacuum cleaner on the other side creates negative pressure to maintain a steady flow and collect waste, preventing laboratory contamination. This pressure differential triggers the three dispersion mechanisms shown on the right. Shear forces from the gas velocity gradient peel apart soft clusters, while interparticle and particle wall collisions provide the ballistic impact necessary to shatter hard agglomerates. This combination ensures that even cohesive powders are fully dispersed into the primary particles before they intersect the laser beam. We have covered the technology. Now, let's determine your specific configuration. This decision tree maps your sample's physical constraints to the correct engineering solution. Start at the left with the first principle, solubility. If your material dissolves in the carrier liquid, you must follow the upper path to the dry methods, selecting the BT912 for bulk powders or the BT903 for scarce samples. If the sample is stable in liquid, follow the lower path. Here, the decision splits by chemistry, water versus solvents, and automation needs. Crucially, note the final branch. For any wet application requiring shape analysis, the Peak 1 module integrates seamlessly. This chart ensures the system adapts to your sample, not the other way around. Hardware precision is wasted without software discipline. We structure the chaotic reality of the laboratory into a linear, automatic pipeline defined by standard operating procedures, SOPs. First, we lock the method, ensuring every operator uses identical parameters. This drives the sample preparation and measurement phases, where the system automatically executes the dispersion and optical analysis we previously discussed. Finally, data and reporting is instant and customizable. By automating every link in this chain, we effectively remove the operator variable from the equation, ensuring that a test run on Monday morning is identical to one run on Friday afternoon. This flowchart represents the complete removal of human variability. Once you press Start, the SOP takes physical control, executing a sequential chain from auto-alignment to background measurement without operator intervention. Crucially, observe the intelligence at the sample introduction phase. The system actively monitors the obscuration, signal blocking. If the concentration is too high, it triggers auto-dilution. If too low, it prompts for addition. The cycle concludes with auto-cleaning, ensuring the cell is pristine for the next run. This closed-loop automation guarantees that your results are determined by physics of the material, not the technique of the user. Recall our discussion on the observability limit of irregular particles. We now translate that theoretical necessity into a practical software workflow. The 2600 Plus treats the imaging module not as an external accessory, but as an integrated sensor. To activate it, you simply check the Enable Combine Test box in the parameter settings. There is no complex calibration or hardware swapping required. The software automatically synchronizes the laser and the camera systems. With this single click, You force the system to cross-validate the diffraction data with image analysis. This ensures that the sensitivity to oversized particles and shape information is automatically captured, making comprehensive characterization a default setting rather than a complex experiment. Raw data is useless if it does not align with your specific quality standards. While the instrument measures scientifically in microns, your factory floor might operate on mesh sizes or specific cut points. The custom classification function bridges this gap. For example, in the cement industry, the critical quality metric is often the percentage of particles above 80 microns. Instead of analyzing a complex curve, you can configure the system to report that exact value automatically, streamlining your QC decision making. Furthermore, the Saving Simulation Center Panel acts as a translator for legacy standards. It mathematically converts laser data into mesh values, allowing you to upgrade to modern laser precision without rewriting your decades-old sieve-based specifications. In the era of Industry 4.0, a particle analyzer cannot be an isolated island. We engineered the 2600 Plus to speak the universal languages of laboratory automation. Circulate, Modbus RTU, and Modbus TCP. Whether you are connecting to a central LIMS database for archiving or directly to a PLC for real-time process control, the system offers a reliable, standardized digital pathway. This eliminates the risk of manual transcription errors, ensuring that the precision we achieved in the optical bench is preserved all the way to your final quality report. In high-throughput manufacturing, you do not need just a number, you need a decision. The data evaluation function automates this go or not go process by embedding your quality standards directly into the software. You simply define your upper and lower limits for critical parameters like D10, D50, or D90. The system then mathematically compares every measurement against these constraints, instantly generating a visual pass or fail on a report. This removes the burden of interpretation from the operator. It transforms a complex particle size distribution into a clear, binary quality verdict, ensuring that out-of-spec material never accidentally leaves the factory floor. A measurement is only as valuable as its presentation. Your R&D director needs raw statistical depth, while your shipping department needs a simple certificate of analysis. One rigid template cannot serve both. The 2600 Plus solved this with a fully editable report engine. You can drag and drop modules to build custom templates, hiding complex graphs for external clients or highlighting specific parameters like D50 for internal QC. Furthermore, we ensure convertibility. With a single click, you can export these reports to PDF for secure sharing or to Excel and text formats for further offline analysis. This ensures the data leaves the instrument in exactly the format your workflow demands. A report should not just be data. It should be a direct answer to your industry's specific question. We allow to strip away the noise and highlight the customer critical metrics that drives your processes. Consider the diversity of applications. A mining engineer controlling a grinding circuit does not care about mean diameter. They need the D80 or P80 to ensure liberation efficiency. A chocolate manufacturer needs to know the fraction above 35 microns, as this specific coarse tail determines whether the product feels smooth or gritty in the mouth. The 2600 Plus allows you to configure these specific parameters as headline metrics on your report alongside your own corporate branding. This ensures the document speaks the language of your quality manager, not just the language of the instrument. In mining and soil analysis, a single method is often insufficient. Laser diffraction excels at fines, while traditional sieving remains the standard for coarse fractions. Historically, these datasets were incompatible. The 2600 Plus software bridges this gap with sieve laser fusion. You simply input the mass fraction data from your physical sieves, and the algorithm mathematically stitch it with the laser diffraction results to create a single continuous distribution curve. This empowers engineers to optimize processes based on the entire particle population, from flotation slimes to crushed ore, in one unified, actionable report. We have discussed the optics, the dispersion, and the software automation. Now we verify the result. This is the proof of concept for the entire system. According to ISO 13320, a qualified instrument must maintain repeatability within 3% for the D90. The Bettersizer 2600 Plus shatters this standard, achieving repeatability of less than 0.5%. Look at the graphs. 6 consecutive tests, 6 overlapping peaks. This consistency is not just due to the laser, it is the direct result of the smart SOPs removing the operator from the equation. We do not just promise precision, we automated it. We have proven the system is consistent with repeatability. Now we must prove it is correct with accuracy. We validate the trueness of the optical bench using certified reference materials from Duke Scientific. Observe the span of this validation. We test standards ranging from 100 nanometers up to 240 microns. In every instance, the measured peak, the colored curves aligns perfectly with the certified nominal value. This confirms that the entire optical range, from the lateral detectors measuring the coarse particles to the backscattering detectors measuring the nanoparticles, is calibrated to physical reality. Accuracy is about hitting the target. Resolution is about seeing the details. Many instruments smooth data, merging close populations into a single broad hump. On the left, observe the tri-model test. We mix the 3 distinct sizes of fine particles and 3 of coarse. The 2600 Plus clearly resolves them as separate, sharp peaks rather than blurring them together. On the right, we test sensitivity, the ability to detect trace contamination. We added minute quantities of 20 micron particles to a 5 micron base. Even at extremely low concentrations, the system picks up that second peak immediately. This ensures that if you have a needle in a haystack, like a few large particles in a fine powder, we will find it. We end here not with a list of features, but with the new insights the Bettersizer 2600 Plus bring to your industry. We are moving beyond simple particle size to process intelligence. In batteries, we move from measuring average size to ensuring safety. By detecting a single large agglomerate that causes a short circuit, we protect the battery's integrity. In pharmaceuticals, we move from volume distribution to predicting bioavailability. By precisely measuring the fine fractions that drive dissolution rates and detecting the unwanted agglomerates that ruin content uniformity, we guarantee consistent drug delivery. In mining, we move from data slows to total process control. The seed fusion function unites the mine and the mill into one efficient workflow. In ceramics, we move from standard QC to ensuring durability. Our high resolution detects the coarse tail that causes structural cracks. This is the power of the Bettersizer 2600 Plus. It transforms your laboratory from a data generator into a diagnostic powerhouse. Thank you for watching this deep dive into the Bettersizer 2600 Plus. We hope this presentation has shown you how new insights can transform your daily laboratory workflow. If you want to explore the technical specifications in detail, please scan the QR code on your screen right now. It will take you directly to the product page with a brochure and more resources. If you have specific questions about your own samples, whether it is battery materials, ceramics, or pharmaceuticals, please leave a comment below. Our application experts will get back to you with an answer. For more content like this, don't forget to subscribe to the Bettersize channel. I'm Weicheng Gan. Thank you for choosing Bettersize, the better particle size solutions.